I was asked what was after chapter 13. Change. This Introductory to Discrete Mathematics by V.K. Balakrishnan is the textbook that was designed for the computer science math course. And because it's designed to span both some linear and some graph theory, I used that book and I came up with a couple that I thought were enough to mention in this course. So I took two chapters, in chapter 4, chapter 5, and put them on our reference files page. So you've got the text of the two chapters we're going to look at. And an example for a piece we're going to do on Friday, the Floyd-Warshall example. These three files are the next 3 days. Advantage on this array. Prim's algorithm. How did Prim's algorithm work? We were pulling smallest numbers. We were trying to find the minimum spanning tree. Now, when we did it with a matrix, we were looking for the lowest count in each set, and it was based on the weight of the edge. Right, instead of degrees, we looked at weights. But that's just one version of how we can apply that matrix. And that matrix really looked at what's connected to what and how much it costs. That's what the weight of the edge was. If I just what's connected to what, then I can create a different matrix. Whether I'm looking at a digraph, a multigraph, a pseudograph, or a simple graph, the idea is the same. So here is a straightforward graph. A familiar looking straightforward graph. Where did we see this one before? That was our Euler idea, whether or not we could travel over the bridges. That's the bridge of Königsberg. Yes, in Germany. So my goal here is to turn this into a matrix. Now, because this is a multigraph, I'm going to do this differently than for a simple graph. So we'll do several different variations on this idea. So I'm going to start. What I really have is a listing of edges. But I want to list vertices. So I need to lay out a 4x4 matrix. 4 vertices. What order do I lay them out with depends entirely on my choice. I don't care what order you put them in. It literally doesn't matter. But in order for me to keep it straight, I'm going to write it on the outside edges, across the top row and down the left side. In this case, I'll do that because these are not numbered vertices. They're labeled with letters. I need to keep it straight. North, east, south, west. North, east, south, west. Is north connected to itself? No, there's no loop there. Is north adjacent to east? Is north adjacent to south? Is north adjacent to west? However, this is a multigraph. There are 2 edges connecting north and west. I'm going to put a 2 there. If this was a simple graph, I would simply put a 1. If this was a pseudograph, I'd have loops, right? Then north could be connected to itself, couldn't it? East. East is connected to everything but itself, and with just 6 edges. Please note, this is an undirected graph. If north is connected to east, then east is connected to north. Symmetry, which means I not only can fill in across the row, I can fill in down the column at the same time. South. Is south connected to itself? Nope. Is south connected to west? Twice. Is west connected to itself? This is called the adjacency matrix. If I have a simple graph, every entry in the adjacency matrix is 1 or 0. By the way, that's even true in simple graphs with loops. But that really doesn't make sense because simple means no loops, no multiple edges. There's a little bit of a crossover here. As long as I don't allow multiple edges, 1 or 0. This matrix is symmetric because it's undirected. In a digraph, nope. Could it be true in a digraph? So yes, only if the digraph itself is symmetric. Every time I have a V to U, I have a U to V. Otherwise, my digraph could be all over the place. If my vertices are already numbered, then it makes sense to me to put the rows and columns in numerical order. What's the adjacency matrix for this graph? And I promise I didn't pull this out of my ass. Just copied that out of the book. Where row I corresponds with vertex I, column I corresponds with vertex I. I've got a loop. Why do I know I have a loop without looking at the picture? Vertex I is connected to itself. Perfect. The matrix can inform me about the graph. Again, this is a symmetric matrix. We have an undirected graph. Gesundheit. What's the row sum for row 1? Which also is the degree of vertex 1. Row sum for row 3, which is degree 2. Well, degree of 3, right? Why did I skip row 2? I need to make an exception when I count the row sums or the column sums. I need to count twice, which means all the diagonal entries have to be doubled. So really, when I count the sum across each row, I need to know which row I'm in, so I can make sure to double the appropriate entry in this. So in one sense, this 1 really should be a 2, shouldn't it? That would make my life easier. Every adjacency matrix strictly a binary matrix. All of the entries are 1 or 0. Phooey, according to this book, which, by the way, in the actual text of the book, gets this wrong, which pisses me off to no end. I would like to point out to you a quote from page 126. In this graph, vertex 1 and 5 are odd. Why do I know that's absolute bullshit? If I had 3 odd vertices, I'd have broken the handshake principle. Really? You wrote a book. You didn't get it, even though you have the handshake principle in the previous chapter? Yes, I have submitted an error report. It's not a terribly old book. Why am I still using it if I know it's done? Because it's still one of the better books out there. Questions? What changes if I have a digraph instead of a regular graph? Again, I stole this from the book. Yes, there's a loop on it. I want an adjacency matrix for this too. It's still a 5 by 5 matrix. I still only have 5 vertices. That part didn't change at all. But now, I'm going to ask my adjacency question differently. The ijth entry in the matrix A is equal to 1 when? It's either a 1 or a 0. When is it a 1? So is 1 adjacent to 1? Is 1 adjacent to 2? No, but 2 is adjacent. Oh, okay. I can go from 1 to 3, from 1 to 4, but not from 1 to 5. 2 to 2, 1, but not to 2, nor to 3, yes to 4, yes to 5. Okay, so now I have to fill out either across the rows only or down the columns only. When I go down the columns, I'm doing adjacent from. Across the rows, I'm doing adjacent to. 3. What's row 3 look like? I only go from 3 to 2 and to 3. 4 goes to 3 and nowhere else. And 5 goes to 1 and 3 and 4, not to 2, not to 5. Digraphs change my definition for degree. Add up the numbers in row 1. What does that number represent? The out degree. And if I add up column 1, the in degree. And how many 1s appear in this entire matrix? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. Because I don't have to worry about doubling the degrees for the loops, because I counted the outs and the ins separate from one another. Huh. Here's an adjacency matrix. Two questions. Is this a digraph or a regular graph? Why? The matrix is symmetric. Does it contain loops? Why, Reese? I'm sorry? There are 1s on the diagonal. There you go. Draw me the graph. Now, I just made this up, so I don't have a picture yet. And here's the best part. I didn't tell you how to lay out the vertices. You could make them a square. You could make them a triangle with one in the middle. You could make them a diamond. I don't care. But because this is an undirected graph whose matrix is known, there is a graph here. Whatever graph you choose to draw will be isomorphic to the one I draw. There you go. Regardless of how you labeled it, you've drawn effectively this picture. In a sense, there are exactly as many distinct graphs. Notice I did not say non-isomorphic graphs, distinct graphs, as there are binary n by n matrices. How many possible ways could you fill in the matrix A? A 4 by 4 matrix. A lot. It would be 2 to the 16th. 65,536 different ways. What the? Of them are different. That's a bigger problem, isn't it? And that's one of the problems we had way back when we started talking about graph isomorphisms, didn't we? We said there was no single guaranteed way to know if two graphs were isomorphic or not. You might say, well, maybe they give you the same matrix. But if I change the labelings here, that's the permuting the rows and columns of that matrix. And those are distinctly different matrices for exactly the same graph. All I do is relabel. Questions? I called it the adjacency matrix because it was indicating whether or not two vertices were adjacent. It was a non-zero number when our vertices were adjacent. Incidence. Incident. I'm back in September, chapters 1 and 2. The hell's incidence? Aha! So edges are incident to vertices. Okay, so if I a graph G of order n and size m. Order is number of vertices, size is I want to write down an n by m matrix. Each column is going to represent an edge, and each row is going to represent a vertex. Rows by columns. Now, the only way to do this is to have stuff labeled. And this time, not only do I need to have all of my vertices labeled, I need to have all my edges labeled. I'm going to make life easy and label everything with numbers, or I'll label everything with lowercase letters and we'll do it all in alphabetical freaking order. So here is my graph with 5 vertices and 6 edges. If every row represents a vertex, every column represents an edge, I've got a 5 by 6 matrix. How do I write edge 1 connects vertex 2? Here's the basic block for my matrix. A row for each vertex, a column for each edge. This edge, edge 1. I need to indicate on here that it only deals with vertex 1 and 2, doesn't deal with 3, 4, and 5. Do the same thing we did for the adjacency. I'll put 1s where it touches and 0s where it doesn't. Keep going. Edge 2 connects. But wait, so does edge 3. Parallel edges are okay here. This is a multigraph, not a simple graph. It's got loops. It's a pseudograph. I got all sorts of stuff going on here. Edge 4 goes from 1 to 5. Edge 5 goes from 2 to 2. And edge 6 from 2 to 4. Now I rigged this. Every vertex has a row sum equal to its degree, with one exception, the row with the loop, and a column sum. It doesn't tell me squat, because what's the column sum for every column? Except the loop, it's always 2. An edge can only go between 2 vertices. Column sums are useless. Row sums, on the other hand, indicate degree, except for loops. And when I say I rigged this in a fashion that if you notice, as we go from left to right, they're in order. 1, 2, 1, 3, 1, 3, 1, 5, 2, 2, 2, 4. As ordered pairs, they're in alphabetical order. Go by the first number first. When the first number is tied, go by the second number. We call that dictionary order when we use letters. But in this case, because it's the exact parallel, math geeks decided the dictionary was too easy of a word. You'll love this. Lexiconographical. What the hell's a lexicon? A lexicon's a list of words. Somebody decided dictionary was too easy. We're going to use a fancy word instead of dictionary. Dictionary word. How does this change in a digraph? Without loops. Here's a digraph, no loops. Parallel edges, yes, no loops. I want an incidence matrix. But because this is directed, I'm going to need to change stuff. I need to change something up there in the matrix indicators to indicate out versus in. This is, by the way, why we didn't bother with loops in this version. Because the easiest way to indicate out versus in is with sign. I go out from something, I'm losing. I go into something, I'm gaining. So all of my out is going to be negative, all of my in is going to be positive. If the edge comes out of vertex I, we get a -1. Goes into vertex I, we get a +1. Give me a matrix for this digraph. Do you now see why the loops are a problem? How do you indicate a loop? It should have a plus and a minus in the same spot. plus 1 minus 1 is 0, but that would tell me there's no edge there. Edge 1 goes out of vertex 1 into vertex 2 and doesn't touch vertex 3 or 4. Edge 2 goes out of vertex 2 and into vertex 4, doesn't touch 1 and 3. Edge 3, out of 3 into 1. Edge also out of 3 into 1. Edge 5, out of 3 into 2. And edge 6, out of 4 into 3. Somebody tell me why the edges are numbered the way they're numbered. I rigged it again. Tell me if you see the pattern. I have a negative on the bottom. As we go from left to right, we come out of 1, out of 2, out of 3, out of 3, out of 3, out of 4. We go into, when the first number is repeated, we go into 1, 1, 2. It's in dictionary order again. Sneaky son of a... Almost every I have seen written up this way does order the edges deliberately in that fashion. So I didn't do this on my own. Again, row sums. On their own, row sum doesn't tell me squat. But total number of positive ones in a row, look at the first row. Positives are gains to a vertex. Positives are in. Negatives are out. So if I total the negatives and I total the positives separately, I get the in degree and the out degree. Sorry, out degree for negatives, in degree for positives. I'll just tell you the difference between the two, which hasn't been very helpful to me in anything I've done so far. I don't know why you would want the in degree versus the out degree at this point in time. But I did see things like that in the DiffEQ course, things going out of tanks and coming back into tanks. There was all sorts of behavior like that. There's a lot that could be done with something like that. More coming out. Questions? In this one, the first number goes down. I think of each of these as an ordered pair, right? This first edge goes 1, 4. The second edge goes 1, 2. Helps if I'm reading the right graph. This one goes 1, 3. This one goes 1, 3. This one goes 1, 5. This one goes 2, 2. And this one goes 2, 4. So if you listed those, quote, alphabetically, you would list the smaller first letter, and then you'd look at the next letter. So I would have 1, 1, 1, 1, all of those go first. 2, 2, those go last. Yes? So in order, it would be 1, 2, 1, 3, 1, 3, 1, 5, 2, 2, 2, 4, right? 1, 1, 1, 3, 1, 3, 1, 5, 2, 2, 2, 4. Here, because I have ins and outs, listing them as ordered pairs makes more sense. This is 1, 2. This is 2, 4. This is 4, 3. This one is 3, 2. And these are both 2, 1, right? Sorry, 3, 1. Helps if I can read my own damn handwriting. Put those in order. 1, 2, followed by, is there anything else with a 1 in the first spot? No, jump to 2. 2, 4, followed by anything else with a 2 in the first spot? No, jump to 3. 3, 1, 3, 1, 3, 2, in order, followed last by 4, 3. 1, 2, 2, 4, 3, 1, 3, 1. That's my ordering. In another sense, it makes the patterns of ones go this way from upper left to lower right, but it isn't uniform because I have outs and ins. Here, I can say, oh, you'll never see a 0 in the first row and then see following a 1. Does that make sense? And here, these ones always go down. Here, these ones go down. I didn't expect it to be obvious. And nor is it a commonly used measure of anything other than, oh, that's cool. I have more about this. Because this just tells me what's connected. I want to go move in my graphs. In this graph, can you get from 5 to 4? Not directly, but there's a walk you can take, isn't there? How long is it? There's a geodesic. But you could take longer walks, couldn't you? How many ways can you get from 5 to 4? And how does this or this help me figure that out? We'll talk about that on Wednesday. I'll see you all then.